in a redox reaction, we go from, in a redox reaction, there are elements that transfer electrons, right? In the bonding and moving around of different elements within a chemical reaction, we see an electron transfer or an electron movement. And that happens when an element goes from being like a diatomic to now being a part of a compound, right? There's a change in what has to happen in terms of the charges and things like that. And so we're going to look at what does it mean to be a redox reaction and how do we identify a redox reaction. To do that, we're going to go back to, in Chem 1, we would have studied something called oxidation numbers. Does that at least term sound familiar? Oxidation numbers are almost like pseudo charges. They're not full charges, but they do show us the electron locations kind of within a compound. And so we're going to go back to those and look at oxidation numbers again a little bit and help us identify what's happening in the reaction. In the reaction, are these electrons moving spots from one compound to another? So that's kind of where we're going in this section today. Here's an example of sodium and chloride. Okay, this is an example of a redox reaction. We take basic sodium atoms and basic chloride molecules, and we form now sodium chloride, okay? In a minute, we're going to talk about why this is a redox reaction and what that means, but we've got to take a step back first and talk about oxidation numbers or oxidation states. First of all, before we even get to that, let me go one more step back here. Cl2 is an example of a diatomic. Do you remember how many diatomics there are? 7. Very good. Okay. I can remember if we just talked about that recently or not. All right. So these are all of our rules for oxidation numbers. Okay. These are ones that you should be familiar with and you've seen before. Oxidation state of an atom in an element. Okay. This is not a very good definition your book gave. Sorry. I don't know why I didn't catch this. Oxidation state of a atom in, let's rewrite this a little bit, in an elemental compound. Okay. And so what that means is like if something is bonded with itself, like the diatomics, like an S8, like whatever it might be, those are examples of a situation in which our oxidation number would be 0. So if I had Cl2, the oxidation number for each chlorine atom would be 0. Okay, the oxidation state of an element that's by itself is 0. If I had S8, the oxidation state of each sulfur would be 0 because there's not any uneven distribution of electrons here, right? The electrons are not kind of crowded in one area or another. They are just evenly dispersed within those elements. All right, number 2, oxidation state of a monatomic ion is equal to the charge of the ion. So that means if I had, if I had chloride -1, Cl -1, that means the oxidation state of the chloride would also be -1. It would match the charge. Okay. Oxidation number of fluorine is always -1, right? Remember with our oxidation numbers, there was the big 3. Do you remember talking about the big 3? Fluorine, oxygen, and hydrogen. Good, hydrogen. Fluorine, oxygen, hydrogen. Fluorine's -1, oxygen's -2. And then hydrogen is +1 anytime it's in a covalent compound. Okay? When we're talking about oxidation numbers, the sum of all of the oxidation states of a compound should equal 0 as long as the compound is neutral. Okay? 0 in compounds that are neutral. And I think this probably seems a little arbitrary until we actually get into an example, and then I think it will come back to us a little bit. But that's the rule for that. If our compound has a charge that is not 0, the sum of the oxidation states should still add up to be the charge of that compound. Okay? So let's walk through a couple of examples. I've got some examples listed on your next slide, and I'm going to go out of order because I want to start with an easier example, and then we'll work into a little bit more complex. So I'm going to start here with MnO2. Okay, and I'm going to write it a little bit bigger so I've got some space here. But MnO2, do you know what it's called? So I'm gonna look at my compound here, MnO2. Okay, does it have one of the big 3? Yes, it does. Okay. Now, when I write oxidation numbers, I like to put the oxidation numbers up top, and I use the bottom as like my workspace. okay? Each oxygen has an oxidation number of -2 because it's in a compound, right? If it was by itself, then it would be 0, but it's not. It's in a compound. And so how many oxygens are there? So that gives me a total of -4. Does my compound here have a charge at all? Was a charge listed? No. So I need the sum of all my oxidation states to add up to 0. So what number must go there to get that to equal 0? +4. And how many manganese have to split up that +4 charge? Just 1. So that means manganese has a charge of +4 and oxide has a charge of -2. Okay, oxidation states in ionic compounds are basically just their charges, right? In ionic compounds, they are just the charge. In covalent compounds, then we see the electrons move a little bit around, okay? And our oxidation states are different than our normal charges. But that's how you would list that. And then if you were going to ask for the answer, you'd say M, N is equal to +4. O is equal to -2, right? This down here is just our workspace. Up here is where I put final answers. Okay. Let's try another one here that does not have the big 3. So let's try this one. PCl5. Okay, if it does not contain one of the big 3, you choose the most electronegative atom gets to keep its charge. Most electronegative between phosphor and chloride, do you remember? Chloride, because it's going to be whatever one's closer to fluorine. If you still can't remember that rule, whatever one comes last gets to keep its regular charge. Okay? So what's chloride's regular charge? -1. And there are how many of them? 5. So that gives me a -5. So what has to go here? +5. And how many phosphorus have to split that? Just 1. So that means phosphorus has an oxidation number of +5 and chlorine has an oxidation number of -1. Okay, so let's just see this in a Lewis structure real quick. PCl5. Now, are each of these bonds polar or nonpolar? Just take a guess. Based on their electronegativity values, do you think they're going to be polar bonds? I think so, right? Chlorine is really close to fluorine. Phosphorus is a little bit farther away. So what's happening in each of these bonds is that chlorine is pulling the electrons. So it's almost like they each have a partial negative, partial negative, partial negative, right? That's what's happening in each of those bonds. And so if phosphorus have 5 partial positives, that's where the oxidation state is coming from. Okay, remember, they're not full charges. Chlorine's not taking those electrons away, but they are hogging those electrons in the bond. Okay, does it have one of the big 3? Yes, and I'm combining them. Fluorine, we said, was -1, and there's 4 of them, so that gives me a total of -4. And so sulfur then has to be what? +4. Right, pretty simple, right? The bottom, again, is just our workspace, so if you can figure it out without doing out all the math, fine, but there was no charge listed here, so I know that has to equal 0. Which makes this a +4, and it splits it between just 1 sulfur. So we get a +4 for sulfur. Yes or no? Yeah, okay. We kind of make this box. Do you remember that pattern? Right, we start here and we make the box. Okay, let's try this one. Carbonate, CO3 -2. So this one has a full charge now. Our compound has a charge. Oxygen, we said, is -2. That gives me a -6. And so instead of adding them up to 0, I want all my oxidation states to add up to -2. I want them to add up to the charge I was given. So what number has to go there to get that up? And it gives you +4. So carbon is going to be a +4. Okay. Last one here is a little trickier because it's got 3 different elements happening. So let's pay attention here. K2Cr2O7. Okay, when we've got 3 elements, our goal is to work from outside in, from outside to in, okay? So we're going to go oxygen first, then potassium, and we're going to leave chromate until the end. All right, oxygen's one of our big 3, so it's going to go first. -2 times 7 is -14. Then we're going to jump over to potassium. Since potassium is a metal and it's forming part of an ionic bond, it gets to keep its regular charge. And so potassium's regular charge is +1. There's 2 of them, which is a total of +2. So what number has to go in the middle there to get that equal to 0? +2. No, not +2, +12. I'm sorry. And how many chromiums are splitting that +12? So we're going to divide on our way up here, and we're going to say that each chromium has an oxidation number of +6. So you multiply on your way down and divide it on the way back up, right? 2 chromiums have to split that +12, and so that means they each have an oxidation number of +6. Okay, in a redox reaction, we said there is a transfer of electrons. That transfer of electrons might cause an ion to form. It might cause a change in an ion. It might cause it to go from the most electronegative to the least electronegative, or whatever it might be. It might cause this change. But what we need to remember is that anytime we see a loss of electrons, it is called an oxidation. Oxidation has happened when we have a loss of electrons. Anytime we see a gain of electrons, we call that reduction. Okay, so we use this acronym called oil rig. Oxidation is loss, reduction is gain. Okay, so I want you to write out that acronym, oil rig. Okay, oxidation is loss, reduction is gain. And you just have to tell yourself of electrons, right? Oxidation is loss of electrons. Reduction is gain of electrons. So a compound is going to have been oxidized, or a compound is going to have been reduced, or an element is going to have been oxidized or reduced. We're going to be able to identify that in each one. People ask you about oxidation or reduction. If a compound or an element has been oxidized, that also means it is the reducing agent. So that means if it loses its electrons, it's then giving those electrons to something else, right? It is causing something else to be reduced. So let's say that again. If something is being oxidized, it is losing its electrons. Those electrons have to go somewhere. Someone else has to gain them. And so that whatever has been oxidized is now called the reducing agent. And it works the other way around. The agents, I don't ask you a lot about, right? I want to know what element has been oxidized here, or what compound has been reduced. But the actual reducing and oxidizing agents, I'm not so concerned about. Okay, but your book likes you to know that term. So I want you to see that in here as well. Okay, so this next slide, just a reminder about what are the oxidizing and reducing agents. But let's go ahead and try some practice here with both of them, even though I'm not going to ask you about the agent a whole lot more often. Okay, I'm going to start on this first one here. Sorry, I didn't realize I didn't give you very much room on your slides to do them, so I apologize. Here's how we're going to go through this. We're going to just go through and assign an oxidation number for every element. We're going to go through and assign all of the oxidation numbers. Let me zoom this in a little bit here. Okay, we're going to go through and assign our oxidation numbers. So, zinc by itself, that is an element on its own in a compound, so it has an oxidation number of just 0, right? An element by itself has an oxidation number of 0, because think, is it sharing electrons unevenly anywhere? No, right? It's not taking on a pseudocharge, it's just by itself. All right, HCl, does it contain one of the big three? And we said hydrogen is plus, so what does chlorine have to be? -1. Okay, so hydrogen's +1, chlorine is -1. Let's come over here to zinc chloride. It does not have one of the big three. So which one gets to keep its regular charge? Chloride is -1, and there's 2 of them. So that means that zinc has to be +2. And it's ionic, right? So that's zinc's normal charge anyway. But that's our charges there. And then now hydrogen is by itself. It's in a compound, but it's by itself. So what's hydrogen's oxidation number? 0. Okay, that's rule number 1 in our oxidation state rules. Okay, if an element is by itself, has an oxidation state of 0. So now I want you to look, are there any elements that changed oxidation state? Any elements in particular that changed oxidation states? Zinc did. Okay, so zinc went from 0 to +2. So did it gain electrons or lose electrons? Think about what electrons are. What charge does electron have? It became more positive, right? So it lost electrons.
How is hydrogen not bonded to
Say it again.
How is hydrogen by itself? Isn't it bonded to hydrogen?
It is, but if it's a single type of element in a compound, still has an oxidation number 0. Yeah, because they're not going to share electrons unevenly, right? They're the same element, same atom, right? Same type of atom. So yeah, so there's no way that one hydrogen is pulling on electrons more than the other. Okay? Yeah.
So would the same thing apply to like O2 and F2?
Yes. Yep. Okay, so if zinc lost electrons, has it been oxidized or reduced? Oxidized. And so therefore it is also the reducing agent. Right? If it's been oxidized, it is also the reducing agent because it gave up 2 electrons. Now, those electrons couldn't have gone to nowhere. Some other element had to have changed. Some other element had to have been reduced. So which was it? Hydrogen. Hydrogen goes from a +1 to a 0. Now, that only looks like there's 1 electron transfer. But look, here's our coefficient here. We have 2 of those hydrogens that are going. So that it's not a way, it's just a kind of a way for you to check it. You don't have to go back and prove that where all the electrons went, but you do know that going from +1 to 0 is a gain of electrons. And so that means it is being reduced, which means it is also the oxidizing agent. So in this reaction, we went ahead and identified all the oxidation numbers. Is there any change that's happening here? Nope. So all we have to do here is put not a redox reaction. Remember, RXN is an abbreviation for reaction. It just is not a redox reaction. Right? There's not a transfer of electrons. Okay. Why don't you try the last one on here on your own? I think it is. The coefficient doesn't change the oxidation number, no. Okay, this one is kind of tricky because what is it that's changing here? Copper is changing into 2 different things. And so I don't usually give you ones that look like this, but this compound right here is acting as both the oxidation and the reducing agent, right? It's causing the change for both. Okay, I only have one reactant here, so it's going to be acting as both the oxidation and the reduction agent. Okay, because it's causing copper to go to +2 and to +0, right? So copper 2 is being oxidized and copper is just being reduced.